Welcome back. In this video, we are going to learn about two fluid properties which got a lot of engineering or practical applications: surface tension and vapor pressure. So to start with, you might have seen these insects walking on the surface of water or even running on the surface of water, and they don't sink. And another case is about, when you cook in a very high altitude, like maybe on the top of Himalayas or some very high mountain, it will be very difficult to cook, especially cooking vegetables or meat. What is the reason behind this? So let's try to explore by understanding these two properties in detail. So let us start with surface tension, which is denoted as sigma or sometimes also as gamma. And we are already familiar with this property if you have played with soap bubbles, or if you have played with this boat, right, the paper boat, which is fueled with some liquid soap. So if you have played with all these, you know the surface tension, you have used surface tension in your day-to-day activities. So what is the surface tension, right? So actually surface tension you can look into surface tension from two different perspectives. One is from an energy point of view and another is a force point of view. So there are two different definitions. So from an energy point of view, it is the energy required to create a surface that is called as the surface tension. So for example, let's say you are trying to cut a block of butter, right? You're cutting a block of butter, and now you're cut into two pieces. Now you have applied a lot of energy, right? Not a lot, at least you have applied some energy. Where is this energy going? If you look into this from a mass conservation point of view, mass is conserved. It is broken into two pieces, and the mass is conserved here. And there is nothing else, right? It is not melting, or there is no chemical reaction happening, or there is no heating up happening. None of this. So where is this energy going? The energy is going to create that surface. So you have two surfaces now, one on the left hand side and one on the right hand side. So you created two surfaces. So this energy which you spend to create this surface is called the surface tension from an energy point of view. So it got the unit joule per meter square. Okay, so that means if it is 1 joule per meter square, it requires 1 joule of energy to create 1 meter square of this surface. So when you look into a chemical engineering point of view, so what actually happens, right? When you're creating a surface between two different type of molecules or within the molecule itself, right? You're trying to create a surface. What happens? You're trying to break the bond, the chemical bond. So this is where you are spending your energy. So you break those bonds and then try to create an interface. Now let us look it from a force point of view. So if you define surface tension from a force point of view, it is the property of the liquid to shrink to a minimum surface area due to the tug of war between the molecules. So what does it mean, right? So let us consider an interface, a surface of let's say a liquid. So you have a liquid droplet fallen on a surface. So let's say it's water, and you got a lot of inner molecules. A lot of molecules are there of water inside that, and they are getting attracted to each other, right? So all these molecules get attracted. The similar molecules get attracted, and on the top of this interface you have air, or we can consider vapor. Let's say air here, and you have they have their own attraction. And so when you call it as in the the terminology for these forces, it is adhesion. Adhesion means it is the force of attraction between the unlike molecules. So let's say here water and air. If water and air is attracted, this is adhesion force. It's between unlike molecules. And cohesion means the attractive force between the like molecules. This is here water and water, right? So, and what about the molecules on the surface? So you have the interface, and on the surface also you have the water molecules, right? So what happens to these molecules? Definitely you have the cohesion. These are getting attracted by other molecules inside, and there is also adhesion, right? There is an attraction between air and water, and this is basically a weak adhesion. This force is much weaker compared to the cohesion force which is there inside. So then what will happen? This is the tug of war. So then you have a resultant force. You have a resultant force on the surface which will make it like a membrane. So you have a resultant force pulling it. This is nothing but the surface tension force. So you have the unit of this surface tension force as Newton per meter. You can basically convert this to Newton per meter as well. So you define it as Newton per meter. So where is this meter coming from? This is because this is acting on the perimeter, right? This is considered acting on the perimeter of this surface. So this is why you can say that, when the insect is on the top of water, it actually, works like a membrane, and then insect doesn't go down or it doesn't sink. Now let us look into an important concept, the contact angle when it comes to surface tension. This is very important for our practical applications. So you need to understand how, how we get this contact angle, right? So let us say there is a droplet which is on the surface of wood or metal or glass. So, and what happens here, right? So you have this droplet, something like this, which looks like it is wetting the surface, and this is solid, and this is liquid, and this is the gas, right? You have something like this, and let's say this is under equilibrium. So there is a force, different forces are acting here, right, on the surface tension. So let's say this is the force, the surface tension coefficient acting in this direction in equilibrium is sigma gs. This is between the gas and the solid. And you have in this direction, the tangential direction, this is sigma gl, and you have also in this direction, which is nothing but sigma sl between the solid and the liquid. Now if you take a force balance in equilibrium, so let's take the force balance in the horizontal direction. So you can say that sigma gs is equal to sigma sl plus, if this is an angle theta and this angle is called the contact angle, so we have to take the cosine of this, the sigma gl cos theta. This is the component acting in the horizontal direction. So then from here you can get the cos theta is equal to sigma gs minus sigma sl divided by sigma gl. So basically you get this angle, this the contact angle based on the surface tension coefficient between the liquid, and the solid, and all these combinations. So that means you can vary this contact angle if you can vary the surface chemistry, right? So that is how people try to make different contact angles, right? So you can vary this, you can modify the surface, and you can play around this phenomena. For example, if you have something like this, this is our example where it is looking like it's wetting on the wall. So here the contact angle, if you notice, this angle is below 90 degree. It's an acute angle. So if the angle is below 90 degree, this will wet on the surface. So, if you take some examples like alkanes or petrol, so if you put a droplet of petrol, it will just spread, right? These angle of, contact angle of these kind of liquids are very, very tiny, very, very low value, like 1 degree, 2 degree in that range. So that means, it just spreads on the surface. So these are called as hydrophilic because, it is spreading, it is wetting the surface. And if your contact angle is above 90 degree, the liquid does not wet the surface. These angles are above 90 degree, and these are called as hydrophobic. It's, it's against attraction, right? It's hydrophobic. And you can really use this phenomena, you can change the surface chemistry and then create this kind of contact angle, and it can be used for practical applications. So for example, we have hydrophobic surfaces, there are paints, you can create some coatings on the windshield, for example, on the car, and then you can make it hydrophobic, water will not be wetting. You can create hydrophobic kitchen sinks, you can create hydrophobic paint, so many applications are there with this wetting phenomena. Now another important thing is about it's an extension of the same application. This is again it's called the capillary effect, or capillary. You know already about this. Like if you put a straw, right, or a very thin or a very small diameter tube in liquid, you can see the level gets rise, right? You'll see the water level going up. And you can use this phenomena, especially when it is low contact angle, the same effect. You can also connect it with the adhesion force and the cohesion force, and you can try to explain that. But basically, it is the same phenomena. And if you have these kind of very low contact angle, what basically happens is it is wetting the surface, or you can see a meniscus, which is in this concave shape. And for example, water in a glass, you can see something happening like this, and the level gets raised. And also this level, also you can see that when the diameter or the radius of this tube is smaller, the level gets even higher. And if you use another fluid like mercury, where the contact angle is the other way around, or you can say that the cohesion force between the molecules, the mercury molecules, here in the case, you can take an example of mercury. So this cohesion force is quite, much higher than the adhesion between mercury and the glass. So in this case, the contact angle is more than 90 degree, and you can see that it's not rising here. The level is not rising. The meniscus shape is also different. It is, in a convex shape, and it is going down. Height of this capillary rise based on the surface tension coefficient, you can write it as H is equal to 2 sigma cos theta divided by rho of liquid G multiplied by the radius. So here sigma is the surface tension coefficient, theta is the contact angle, and rho L is the liquid density, where if it is water, you have to use the water density. If it is mercury, it is the mercury's density. G is the acceleration due to gravity, and R is the radius of this capillary tube. So if you have a smaller radius, the H will be higher because it is inversely proportional. Okay, so and you can see this use of surface tension in all these applications, like engineering applications like atomization and spray formation. So here you can see the impingement of two jets to form particles or the spray, right? So it is breaking down into smaller and smaller tiny droplets for increasing the surface area. So you will use it for engine applications and many other applications for preparing for paint, and other applications are there where you will use atomization, right? So you will be breaking down the liquid into tiny droplets. So the shape of this droplet all are defined based on the surface tension. So another application is like if you are putting a droplet and this splash formation, right? This crown formation, this is again here surface tension is very important. The shape of it, and these are all driven through the surface tension force. And this one is very interesting, research from the group from IISc. So here it is about the soul of a bubble, right? So a soap bubble. So at lower Reynolds number, you see how it is behaving, and at higher Reynolds number, it's a turbulent air jet inside, and at a lower Reynolds number, you can see it's oscillating. It's a soap bubble, and you're filling in air inside. So you can see the vortex structure and all those phenomena. Again, if you want to learn these kind of phenomena, the surface tension is going to be a very important property which you have to consider. So now you may be wondering how I know, right? Which application I need to consider surface tension, because surface tension is always there. It's only about whether you need to consider surface tension or not. In some cases, surface tension force may be very, very less or very tiny compared to, let's say, other forces. So the best way to deal with this or understand whether surface tension is required or not is to check or to calculate the Weber number. The Weber number is nothing but the inertia force divided by the surface tension force. So that is nothing but rho v square velocity and the characteristic length, whatever be the characteristic length, if it is a droplet, the droplet length, or if it is a flow through a microchannel, then the diameter of that channel. So whatever is the characteristic length, consider that length divided by sigma. So this is your Weber number. And if this Weber number is approximately 1, that means the surface tension force is almost the same as the inertia force, right? So otherwise inertia force will be too high, and the surface tension will be much less than the inertia force, and you don't need to consider it at all. So if the surface tension force is really of the same order of magnitude compared to the inertia force, then you have to consider Weber number. So if it is around 1 or less than 1, definitely you need to look into surface tension. Okay. So that's all about surface tension. Now let us look into the other fluid property. So the next fluid property is vapor pressure. It's also got a lot of engineering applications. Okay. So what is this vapor pressure? Let us consider a container or a closed container, and you got some liquid filled in it. Let's consider let it be water. Okay. So you have water and you have a closed container here. And what happens, right, when you're putting water in a closed container, the the liquid starts becoming vapor. So there will be evaporation happening, right? So evaporation happens always. There is evaporation, and the liquid is getting evaporated. The vapor formation is there, and since it is a closed container, what happens? Eventually, there will be also condensation happening. So the molecules are evaporated, and then some of these molecules are coming back to the liquid form and in the form of condensation. So at equilibrium, what happens? The evaporation is equal to condensation, right? And at this equilibrium, you will see that these vapor molecules are going to apply a pressure, right? A normal force or a pressure on the surface of the liquid. This pressure at equilibrium is called as the vapor pressure. So at equilibrium, the pressure exerted by the vapor molecules on the liquid surface is called as the vapor pressure. It got a lot of engineering applications, especially like problems or phenomena like boiling or cavitation. So all these phase change process, vapor pressure is very, very important. So, and its unit is Newton per meter square. It is the same unit as pressure. It is, but it is a fluid property. Every fluid is going to have different vapor pressure, and it is also a function of pressure and temperature. Now let us look into the phase diagram, and it from the chemistry, right? So phase diagram, here it is the plot between pressure and temperature, and we are looking at different states or different phases of one particular matter. Right here we are looking into water. So water got solid, which is ice, and it is there in the liquid form, and it is also there in the vapor form. And we also know about the triple point, where everything, all these different states are existing or coexisting at one particular pressure or temperature. So, and the important thing here is the yellow line. The yellow line is the vapor pressure line. So that is the one which is the border line between liquid and vapor. So that pressure value, you can see that is changing with respect to temperature, right? And so that pressure value, that particular pressure value, is what is important for us. That is the vapor pressure. So let us consider one point in the liquid phase. So that pressure temperature combination, at that particular pressure temperature combination, it is going to be in the liquid phase. So let us say it is at atmospheric pressure. So at atmospheric pressure, you have, let's say, if it is water, let's say maybe 50 degrees Celsius, 60 degrees Celsius, this is in the liquid phase. So it is at this liquid phase. Now what you are going to do? You are going to heat it. Let us increase the temperature keep on heating this, from 50, 60, 70, 80 like that. Let's increase the temperature. Then when it reaches one particular temperature, that is the, this temperature, it starts boiling. So basically what is happening is it is reaching the vapor curve, right? At this point, this particular phenomena is nothing but the boiling, and at this point, this is called the boiling temperature. This starts evaporating or boiling, or a lot of vapor formation is there. So the liquid converts to vapor. So this is the boiling process, and which is very familiar, right? We know this boiling process, right? You are boiling it in kitchen. So many applications are there. Apart from our day-to-day activities, there are a lot of applications for boiling. You are using it in industrial application. Boilers are there in the power plants and things like that. So a lot of application, nuclear power plants. So a lot of places you are going to use boiling phenomena. Now to address the question we had, right? When you go to very high altitude, like on the top of Himalaya, it is difficult to cook meat and vegetables. It is you need to put a lot more effort to cook these vegetables and meat. And what is the reason behind it? So we know this phenomena, the boiling process at atmospheric pressure, because we cook at the atmospheric pressure. We sit at our kitchen or at our home, and we are increasing the temperature up to 100 degrees Celsius. Now imagine you are going on the top of very high altitude, right? Very high altitude area, maybe on the top of Himalaya or even higher. So what happens? The pressure reduces. The atmospheric pressure is going to come down. The pressure at that particular height is lower. So when you look at the phase diagram, your vapor pressure, where is it, right? It is going to be lower, and the temperature, the boiling temperature, is going to be lower than the actual boiling temperature. So if it is water, which is what we are going to use for cooking, the boiling point is not going to be 100 degrees Celsius, but it is going to be less than 100 degrees Celsius. Correct? So what is the problem? Then there is a problem in cooking, because your vegetables or the meat, it need to have some temperature to get it cooked, right? So it need higher temperature. Now what happens is, since the boiling point is not 100 degrees Celsius, much before that itself, water starts boiling and the liquid will convert to vapor, and the water will disappear. So that is the problem in cooking. That is why people, it is advised to use a pressure cooker at higher altitude. So you can avoid this problem. Okay, so and now let us look into another phenomena, very, very interesting, very similar. What you are going to do is, instead of heating, what we did here is we have reduced the pressure. Earlier it was heating, we increased the temperature and we hit the vapor pressure curve, the yellow curve. This time we are reducing the pressure and still we touch the yellow curve. And then definitely the liquid will become vapor. So how can you reduce the pressure? This is one important question, right? So how can we, increasing temperature is very obvious. We can understand that. How can you reduce the pressure? This is also possible, and it happens in all the engineering applications or many engineering applications, especially like, if you are forcing some liquid to pass through an orifice, or, you are throttling something. Basically what happens is it will increase the velocity. So when the velocity increases, the static pressure reduces, because the total pressure need to be same. So in this process, when you are increasing the the kinetic energy, or when you are increasing the velocity of the liquid, the static pressure goes down in the same manner. So you can see it in in pumps, you can see it in orifices, you can see it in the any other throttling devices, or the valves, and many other applications. You can see the pressure getting dropped, and it will go below the vapor pressure, or it will touch up to the vapor pressure, and then it will suddenly start becoming vapor. This phenomena is called the cavitation. Okay, and sometimes it is very, very dangerous also, because what happens is these cavitation bubbles will start imploding and remove the material. Okay, so for example, you can see it in propellers. You can see that this is a very interesting cavitation process or phenomena. This is called as vortex cavitation. You'll see that wherever these vortices are there, inside that the pressure is very low, and you can see the vapor formation in these propellers. It can also cause damage to the propeller blade, and you can even see it in the gear system. So if it is immersed in the liquid, so what happens is wherever there is low pressure zone, you can see that at those low pressure zones, vapor formation happens. And this can cause again damage to the material. It can remove, these tiny bubbles will implode and then it will remove the material. So, and there are many other applications of cavitation, right? So, whenever you are dealing with any process where there is phase change, whenever there is, something like cavitation or boiling or evaporation and, condensation. So, these kind of processes, vapor pressure is very, very important fluid property to be kept in mind. So, whether it is simulation or whether it is, experiment or any analytical calculation, these properties are going to be very useful and very important. Okay, so that's all for this video. See you in the next video.